Okay, these are the solutions for the AP Chemistry exam that was given Friday, October the 11th. What I would like you to do on Monday, or you can do it anytime if you happen to come across this over the weekend, is, do it on Monday when I give back the test, is to write out the solutions of the problems that you got wrong. So what I am going to do is go ahead and do these. So this is an ionic compound of sodium and carbonate. So that's a cation, that's an anion. But you don't need to know anything other than how to add and multiply the masses of each. So we're going to start off here with sodium. We have two of those, and each one from your periodic table. Let me just show you. And you're getting it from the atomic or molar mass, since we're dealing with moles. You can call it either one. Then carbon. And oxygen. Okay, and this is going to be 45.98 grams per mole. This is going to be 12.01. And this is going to be 48. Okay, so you can just grab a calculator, just sum those up, and that will be the answer to the problem. And it's 105.99 grams is the mass of that. Although it looks like a molecule, it's an ionic compound. It's called a formula unit. And that gives you that. Okay? All right. Next, asking you to balance an equation. You can do it whatever method you want. If you choose to just do it by counting atoms, I'd like you to write down what the elements are. So we have hydrogen, oxygen, and chlorine. Count the atoms on each side and then count the atoms after. That's what's required to show some work for this. Use the box method, then the boxes are the work that you're showing. So we have one hydrogen on this side, we have two on this side, we have two oxygens here, and we have one here, and we have one chlorine over here and two over here. So you can pretty much balance anything. None of these elements appears more than once on either side. They're all pretty simple to balance, so you can choose whatever you want. Let's go ahead and start at the top with hydrogen. So if I have two hydrogens on this side, I need to put a 2 there to balance out the hydrogens. Now in doing that, the one thing you really don't want to start with is oxygen because it's a lone element. It's not attached to anything. So by balancing this first, it doesn't help you to balance anything else in general. In this problem, you could have, but not generally. You want to stay away from lone elements. Okay, so you got two hydrogens, so hydrogen balances. You got two chlorines, so chlorine balances. Everything's good. If you want to keep track of your atoms as you go along, you could scratch that and make that a 2. You could scratch the chlorine 1 and make that a 2. So the only thing you have left is oxygen. And we have two oxygens here. Okay, so I have two oxygens there, and that's a 2. But in doing that, I threw my hydrogens out of balance. That will happen. That you'll throw something that's already in balance out of balance temporarily. So that means hydrogen over here went to 4. So I have to change this one to a 4. So hydrogen is back in balance. Oxygen is in balance. Chlorine is out of balance now because now we have 4 times 1 is 4. So that became a 4 there. So now I have to add a 2 there to get it back in balance. So now I have, let's go ahead and count up now. So now we have 4 hydrogens, and over here 4 hydrogens. We have 4 chlorines here, and 2 times 2 is 4 here. And then you have 2 oxygens here. You didn't put any coefficient in front of that, so that's going to be 2 here. And over here is 2 times 1 is 2. So I have 4, 2, 2, 4. So that's in balance. So it's 4, 1, 2, 2. And that would be your final answer for that problem. So what limiting reactants problems are about is you'll do these all the time in the real world. You have a certain amount of a compound and a certain amount of another compound, you're going to react those together. But this chemical equation, which is a balanced chemical equation, tells us that if we want to use up all the potassium hydroxide and all the iron chloride, we have to have exactly 3 times as many moles of potassium hydroxide as we have moles of iron chloride. I'm going to write the 1 here because that's the coefficient, even though it's normally not written. So it's a 3-to-1 relationship of moles. So since you're almost never given exactly that 3-to-1 relationship in the case of this equation, you're going to run out of one of these before the other. And so a limiting reactant problem is designed to determine which one's going to run out first, how much of the other one you have left over, and how much of the products that you can produce with that. So what we're given to start with are these amounts of each of the compounds. Now, what some of you forgot, maybe it was just under the pressure of a test, is that chemical equations don't understand grams. They only understand moles. So grams is something that we weigh out on scales in our world, but the chemical equations world doesn't understand that measure, so you have to convert to what it understands. So this is number of moles. So I would like you to write this sentence. Okay, and just remember that you have to have things in moles. It means we're going to have to take these and use these molar mass conversions to go from grams to moles. So go ahead and do that. And for iron chloride, okay, so these are the quantities that you're going to use in the chemical reaction. And I covered up that 1 there. That's a 1.12 moles. So that will fit down here in the chemical reaction. The chemical equation understands these numbers. It does not understand these numbers. So with the limiting reactant, and no matter, you'll find different books do it in slightly different ways than I showed you, that I've been showing you, but it all amounts to you have to run the reaction twice. So we're going to run it once where we assume that we use all of the potassium hydroxide. These are the amounts that we're going to work with in just a second. Then we do it a second time where we assume that we have used all of the iron chloride. Okay, so for the first reaction, this is all of the potassium hydroxide we were given. So we're going to put that in the potassium hydroxide column here and in the row that says all the potassium hydroxide, because 1.12 moles is all that we were given. And we don't need to write moles. Everything here is in moles. Okay. Similarly, for the iron chloride, we have 0.99. We put that in the iron chloride column and in the row where we assume that we're going to use all of the iron chloride. So now what you have to do is you have to simply understand that for every mole of iron chloride, you're going to need 3 moles of KOH. So for this reaction to run entirely, and if I said that the other way around, by the way, for every 3 moles of KOH, you need 1 mole of FeCl. So I need 1/3 as much FeCl as I have KOH. So if this reaction were to run to a completion, so both of them were used up at the same time, then we would need 1.12 divided by 3 gives us 0.37. Some students are getting confused by multiply or divide. Just remember, this is 1 to 3, this is 1 to 3. This one's got to be 3 times as much as this, because this is 3 times as much as this. So similarly, this has to be 3 times as much as this. So we're going to take the 0.99 and multiply that by 3, and we get 2.97. So these units are all in moles. All right, now we go ahead and circle this because we know we have that much. We were given that much. We know we have that much of the iron chloride. So we circle that. And then we go around and we check off, do we have at least this much of each of these? And as I think you all know by now, one of them is going to be a no. One of them is going to run out first. So we go ahead, I'm going to put a Y next to the potassium hydroxide here. Then I'm going to come over here and I'm going to put a Y. Let me go ahead and do this. Put a Y next to the iron chloride here because we circled them because we know we have that much. So now I'm going to come over here and look at this reaction where we use up all of the potassium hydroxide. If we use all 1.12 moles of potassium hydroxide, we're going to need 1/3 that many, or 0.37 moles of iron chloride. Do we have at least 0.37 moles of iron chloride? The answer is yes, we have that much. We know we have 0.99 moles, so we put a Y there. Now we come over here. If we're going to use up all of the iron chloride, that's how much we were given. We're going to need 3 times that much because it's a 1 to 3 relationship. We're going to need 3 times that much potassium hydroxide. That's 3 times that. So do we have 2.97 moles of potassium hydroxide? The answer is no. We only have 1.12. So I'm going to put an N next to this one right here. So now we can start answering our questions. The limiting reactant is the column. It's the compound between one of these two that has the no in it. That's the one that's going to run out first. Okay. We do have 3 times as much. We don't have enough to run this right here. So the answer is this is going to be KOH. You didn't have to write this as a complete sentence. Just give the correct answer. Now, if you had put grams in here, you might have still gotten the same result, but it's totally wrong the way you did it. But you got the right answer. I gave you half of the 20 points for that. But I won't give you full credit because you just got lucky. You could have guessed 50-50, by the way, and gotten lucky doing that too. So I gave you half the points for that. Okay, the next thing is number of moles of limiting reactant used. So that one is not a question I've normally asked, but first you got to identify the limiting reactant is KOH. So the question is, which of these did we run? Which reaction? The reaction that actually runs is this one. It's the one that has the 2 yeses, yes, yes, in this row. So this is the reaction that will actually work. This one won't work. In other words, we have this much KOH and we have this much FeCl3, so we can actually run this reaction. So the amount of the limiting reactant that we used to run this reaction was 1.12 moles. Okay, Next, it asks for moles of excess reactant, not reactant. Now, how much of the excess do we have left over? So we just do a subtraction. We've done this before. We were given this much, but to run this reaction up here, we only needed 0.37. So if you do that subtraction, you end up with 0.62 moles of iron chloride. All right, and the next question then is moles of iron hydroxide produced. So we come over here. Now we're starting to look at the products. The last two questions ask you about products. We know that it was the top reaction that ran, so we only have to put boxes up here. And you simply look for a relationship that's easy to convert. So remember, there's no coefficient here, so that means it's 1 mole. And this one has a 3. So it's saying moles of FeOH that were produced. Well, there's 1 here and there's a 1 here. That's a 1-to-1 relationship. So however many moles this was, that's how many moles this is. So we put 0.37 there. And we can go ahead and put it here. And that's the answer to that. I'm off screen, so let me get down there. Okay, so it's 0.37. It's what we wrote right there. Okay, and finally, the last part is grams of KCl produced. So we're going to have to make a conversion from moles of KCl to grams. So I'm drawing a light line right around everything here. This is inside the chemical equations world. These are all in moles. Now we need to come back out and find some number of grams. That's back into our world. Okay, in order to do that, we need to use the molar mass conversion that's given to you up above. You look up on the up right above the equation. It's 1 mole of KCl Okay, there's your molar mass conversion to get from moles back out to grams. So we'll go ahead and do that calculation down below. So it's 1.12 moles. Okay, moles of KCl cancel, so we're going to multiply these two numbers, and that will give us our final answer. And it's 83.5. All right, and that's how we do that problem right there. So if you didn't get this one right, I would like you to write it out. Be sure you understand it, and we'll do that on Monday when you get to class. Okay, the next problem is an empirical formula problem. Again, anything to do with chemical equations, chemical reactions, chemical compounds has to be put in moles. Grams is what we measure things in, but chemical equations don't understand that, and chemical reactions don't understand that. So let's go ahead and we want to find the empirical formula. So the first step is to do the molar mass here. So we have 2.677 grams of barium times 1 mole of barium. It's just a single element, so you just pick up your periodic table. You come over here, there it is, it's 137.33. And then do the calculation of how many moles that is. And we get 0.019. We'll chop it off at 3 places after the decimal, and that's moles of barium. Okay, do the same thing with bromine. And molar mass of bromine, 79.9. And we get 0.03, rounded to 9. Okay, so now what you do is you have the number of moles of each of those in that many grams. So now you create ratios. You're trying to find the ratio of whole numbers to put as subscripts for this compound. All right, so we start off with barium. So the smaller of the two numbers, of these two numbers, is 0.019. So for barium, that's going to be 0.019 over itself. You always have one of them that's going to be the smallest number over itself. That equals 1. And for bromine, and we get 2.05. And we're going to say it's less than 2.1, so we're going to say that's about equal to 2. So the number for bromine is 2, the number for barium is 1. So since we're saying that is close enough to a whole number, we're done. If it weren't anywhere close, and maybe it was 2.25 or something, or 2.67, you would have to keep multiplying these by a whole number, 2, and then 3, and then 4, until you got a result of both of them that were whole numbers. But that didn't happen in this problem, so we'd have to worry about that. So our empirical formula is BaBr2. Now, there's a sneaky way you could have answered this question. I don't know how many of you saw this without doing all this. And that is by using charge numbers, just to show you sometimes there's more than one way to get to an answer. So a barium ion is in the second group, the second column, so it has a 2+ charge. And bromine is over here. It's in the halogen group, the second to last group. So it has a -1. It wants to take on 1 electron, so it can be like krypton. So that has a -1 or a 1-. Usually don't write the 1, usually just write the minus. But what that means is barium's going to give off 2 electrons. Bromine wants to take in 1. That means you'd need a second bromine to catch that second electron. So we have Ba and 2 Brs. So it's BaBr2. Remember the other little technique you can use? You take the 1, forget about the minus sign, just take the 1, and that becomes the subscript of barium. Take the 2, that becomes the subscript of bromine. You just crisscross the charge numbers, in other words, and forget about the negative or positive signs, and that gives you the same thing. That's another way you could have solved that. If you had done it this way, I would have given you full credit because you did legitimately found that out. Now, is that the empirical or the molecular formula? It's actually, we figured out using the charge numbers, there is actually That is a compound, BaBr2. So it's the molecular formula, but since you can't reduce it any further, you got Ba1 and Br2, you can't reduce that any further. It's also the empirical formula as well. Okay, next up, just a couple questions to see if you knew knew the parts of the periodic table. This was from your colored periodic table. What name is given to the first group? That's these guys over here. And those are alkali metals. If you just wrote alkali, that was fine. It's not alkaline. That is not correct. The next group over is alkaline earth metals. Okay. And what name is given to the 17th group? That's the second to last column. That's these with fluorine, chlorine, bromine. Yes, they're nonmetals, but that's not what that specific group is called. Those are called halogens. Nonmetals do not get credit. Okay, so that's the answer to those two. And then the essay for the ionic bond. I'll give you one that I wrote, but some of you wrote fantastic essays. I haven't finished grading everything. So let me just put it up. And I use lithium fluoride. They're both simple. They're in the second row. It's easy to go. So an ionic bond is formed between a metal and a non-metal. That's always a good way to start these. Is it metals, metals, or metals, non-metals, or non-metals, non-metals, to start off with that. It's not required, but it's just a good way to start. Lithium is a metal with a low ionization energy. Now I define ionization energy, which means it easily gives up its valence electron, and it only has one. Fluorine is a nonmetal with high electronegativity. Now I define high electronegativity, which means it strongly pulls in electrons from other atoms. When fluorine pulls, so you can either say it pulls or it pushes or something like that. When fluorine pulls in an electron, it completes its second orbital and has the same electron configuration as neon, fulfilling the octet rule. So fluorine takes on an electron. It has 8 electrons in its second orbital. That's exactly like neon. That's what's meant by a electron configuration similar to neon, and that fulfills the octet rule. When lithium loses its only second orbital electron, it has a full octet in the first orbital. So it loses the only electron it has in the second orbital. That means its second orbital effectively disappears. So it only has one orbital with 2 electrons in it. But the first orbital can only hold 2 electrons, so that also fulfills the octet rule. So that's just the explanation I'm giving you. So when lithium loses its second orbital electron, it has a full octet in the first orbital and has the same electron configuration as helium. With one more proton than electron, lithium is a positively charged cation. With one more electron than proton, fluorine is a negatively charged anion. The Coulombic attraction between the cation and anion forms an ionic bond. So that would have been a perfectly acceptable answer, but there's many others that you wrote to get that. So that takes care of that. That's a review of the exam, and have you do the ones you didn't get right on Monday. And we will see you then. And all the other videos are up for last week. So go ahead and finish those assignments, please.